Thank you, everyone. I'm very happy to know that everyone is very chatty today. So I'm hoping that we're going to have a lot of questions. So, so welcome, everyone, and welcome back to everyone who's here every Friday. So today I'm very pleased to introduce our speaker of the day and also some other special guests that we have with us. Thank you to everyone who's also joining online, either on Zoom, YouTube, and Facebook. So the seminar is going to be as usual. So we're going to have a very brief introduction for Julien. And then we're going to have his seminar. We're going to start with questions here at the auditorium. And then we're going to, if there is time, also open up the microphone for the people who is online. As some of you might know, these past 2 weeks, there have been some people who have been taking this intensive modeling workshop. So there is some new people in here. So welcome to all of them. Julien is part of that team. I think some of them you will see Lionel, Gwen, and Fabian as well. So for the students at the end of the seminar, if you feel like talking to them, please reach out. We are very friendly people. So I hope that you can connect as well. And well, I'm also seeing some people in here. Esther, who is also back, and I think she's our next speaker for the next Friday. So also, I hope that you can be here. And also Professor Des Barton, welcome. Okay, so I'm going to start with this brief introduction. So Dr. Julien Boucharel is a climate scientist and research fellow at the French National Research Institute for Sustainable Development, IRD. He is affiliated with the Laboratoire for Studies in Geophysics and Spatial Oceanography, LEGOS, in Toulouse, France. He obtained his PhD in climate science from the University of Toulouse in 2011, followed by postdoctoral positions at the University of Hawaii at Manoa and the University of New South Wales in Australia. His research centers on a core question: how does tropical climate variability, especially the diverse behavior of El Niño Southern Oscillation, connect with tropical cyclones, ocean waves, and coastal processes to shape shoreline erosion and flooding? He focuses on ensodynamics, its nonlinear behavior, and its global teleconnections, with a particular interest in how large-scale climate modes interact with storm activity and coastal vulnerability. Rather than studying these phenomena separately, Dr. Boucharel bridges them. Combining observational analysis, theory, and modeling, his work links climate variability across multiple timescales to storm-driven coastal impacts. His recent advances include showing how different climate modes influence global shoreline change, ultimately aiming to improve the prediction of coastal hazards in vulnerable tropical regions. So once again, thank you so much, Julien, for joining us today, and the floor is all yours.
Gracias, Yvonne, for mi introducción. So mi castellano y español es un poco oxidado, so voy a switchar en hablar en inglés. Lo siento. So yes, today I will present the research work I've been carrying out over the past 5 to 10 years. So it's kind of a broad overview of my latest research. And I will be talking about like tropical climate variability, multi-scale, so at over a wide range of timescales, and how those timescales actually interact non-linearly with each other, and how we can leverage those interactions to actually develop some like simplified conceptual framework for seasonal forecasting of coastal hazards. So the main objective of my research was very nicely summarized by Yvonne, is trying to understand the connection between large-scale climate variability, in particular El Niño Southern Oscillation, and regional coastal impacts. So the central question behind all that is like to understand how El Niño Southern Oscillation modulate the activity and intensity of tropical and extratropical storm patterns, and how that can generate waves and in turn impact the regional coastlines in the Pacific and also worldwide. So the question is like maybe why El Niño? Why do I focus so much on El Niño? But because because it's the dominant source of climate variability at seasonal to interannual timescale, as well as the dominant source of predictability of climate and weather at those scales. So I guess you are very familiar with El Niño here, but I will still do a brief overview, background of what it is. So in order to understand El Niño, we have to understand the background condition, the mean state condition in the tropical Pacific that you can see here. So we have like this atmospheric circulation, trade winds that blows from west to east, and that will push and accumulate the warm surface water all the way to the western Pacific to form the warm pool. In turn, those displaced water needs to be replaced in the east, and they're replaced by cold, deep, nutrient-rich water that go up to an upwelling. And you have like this zonal gradient of sea surface temperature across the tropical Pacific, sustained by those trade winds. And those warm water, of course, will trigger convection and precipitation on the western part of the east. So this trade wind sustain as well a thermocline showing with a shallower thermocline here in the east. Now, every 2 to 7 years, on average, those trade winds tend to slow down or even reverse, which will lead to a discharge of those of the warm water from the west to the east, and bringing with them increased precipitation and a very warm sea surface temperature. Associated with that, we have this flattening of the thermocline. That's the El Niño part of the game. So the opposite phase, of course, is La Niña, which is essentially nothing more than the strengthening of the climatological condition. So we can really understand this ENSO dynamics simply by a recharge of warm water in the west during La Niña, and the discharge of this heat content all the way to the east during El Niño. And this discharge dynamics can be simply understood as a simple coupling between the subsurface dynamics, so essentially the depth of the thermocline, and the surface dynamic, the sea surface temperature in the east. So which is also a way to monitor El Niño. For example, I present you like one of the most classic index to monitor, and so which is the sea surface temperature anomalies average here within the Central Pacific box. So associated with this redistribution of heat and convection, of course comes a lot of impacts. So we bring global impacts that can actually vary regionally, and I will focus today on like three impacts. We'll present briefly. First, the sea level. Here you can see a map of sea surface height anomaly or sea level anomaly during the onset of the very strong 97-98 event. What we can see is a rise in sea level in the central to eastern Pacific, so increase in sea level and decrease in sea level in the western part. So we have this seesaw in sea level across the tropical Pacific. During La Niña, of course, the dipole is reversed, and we have an increase in sea level anomaly in the west that can actually trigger some kind of threat to those very low-lying island in the Southwest Pacific, which is my playground actually. I love to and also during El Niño, you have a decrease in sea level that can lead to exposed coral reef and potential coral bleaching. Another example of ENSO impacts, of course, is the precipitation. Here you can see the composite maps of precipitation anomalies in Boucharel winter during El Niño on the top and La Niña on the bottom. And you can see that the precipitation are increasing in Central and Eastern Pacific during El Niño, with more drier conditions in the west. And again, the opposite picture for La Niña, with increased precipitation in the Southwest Pacific and the American continent. So with those precipitation also brings stronger river runoff, which can lead to an increase in sediments delivery through river discharge, at the river mouth. So here's an example of the And third example is storm activity. Here we have the tropical cyclone density anomaly map, composite for El Niño on the top again and El Niño on the bottom, and you can see that we have a very much difference in pattern and intensity of tropical cyclone associated with this shift between El Niño and El Niño. So, for example, increase in the Western Pacific tropical cyclone activity during El Niño, decrease in the Atlantic, and the other way around during El Niño. Of course, those big storms, they're active over a large area of the ocean, and they can generate strong wind and strong wave and swell that will eventually propagate all the way to the coast, and potentially, through the action of wave, amplify vulnerability, as we can see here on this picture taken before and after Matthew, TC Matthew on the eastern coast, eastern seaboard of the US. So you can see that the wave has been So, okay, so here are three examples. So I didn't pick those examples randomly because those three examples of impacts are actually the one that essentially control what happened at the coast. The coastal dynamics will be mostly driven by those three impacts. And you can see here like that the sediment supplied by rivers can redistribute sediment stocks along the beach, and wave and sea level change can increase the coastal water level, and in turn bring potentially coastal flooding. So we have like those three drivers of two coastal impacts, which are the coastal flooding and the coastal erosion. And those two impacts at the coast are actually the main sources of vulnerability for a population that is actually increasingly concentrated over the coastline, with roughly 500 million people living at less than 10 meters above sea level. And that some estimates actually say that without mitigation, that could lead to the displacement of 200 million people by 2100. So what I'm going to try to focus on the rest of the presentation is formulating a new framework, trying to link this scale of variability and trying to understand how ENSO cascade all the way to the regional coastline through the modulation of tropical and extratropical storms, as well as the wave action. So to do that, I will use a bunch of different tools and products. For example, reanalysis products, coupled model, as well as new satellite products of topography and bathymetry that we've been developing in the lab. I also didn't neglect field work throughout my research. As you can see here, a picture of me estimating sea surface height during a swell episode at Boucharel. And the idea behind all that is actually to try to pinpoint and extract the dominant processes and to include them in simplified framework. So I will not be using any of those very complicated models that we've seen over the last 2 weeks. I will be using very simplified framework. Why is that? Because they are really easily implementable for operational tasks, and they're very, very lightweight, so they're easy to run on just a small laptop. So the rest of the talk will be as that. So in the first part, I will provide you with a new way of apprehending ENSO in all its diversity and complexity, and how it affects coastal waves across the Pacific Basin. Then I will show you that the framework can be actually extended to other drivers, not just waves, and actually beyond the Pacific, other ocean basins. And at the end, I will tell you, I will have to admit that ENSO is not the only driver. We have to take into account other climate modes and their teleconnection to ENSO to leverage the framework for an improved scenario forecasting of coastal waves. Okay, so let's jump into the first part. So actually, ENSO and its effect on coastline is not new. It's been noted and documented probably from a long time ago, but at least documented by fishermen during the late 19th century along the coastline of Peru, where they were noting that El Niño would bring more precipitation, more waves, and actually affect their day-to-day fishery activities. But it's not until the, I would say, late 90s to 2000 that we had the first scientific studies, actually, of really documenting and explaining how El Niño would impact specific areas and specific beaches through the action of wave that would lead to increased erosion, as you can see here in California and Australia. But it's not until also the 2010, I would say, 2015, that we have like systematic studies trying to explain how ENSO reach out to the coastline all the way across the entire Pacific Basin. This is documented here, or this is illustrated here, with a map of significant wave height anomalies during the boreal winter, for El Niño on the top and for La Niña on the bottom. So you can see, like, again, this like dipole of ENSO with increased wave anomaly in the Eastern Pacific along the western coast of the Americas, decreased in the Western Pacific, and again, this opposite picture during La Niña. But all the studies, actually, they stayed at this like kind of basic reconnaissance level of El Niño, like this dipole, this seesaw across the Pacific. But I will show you that ENSO is much more than that. Over the past like 15 to 20 years, there's been a renaissance of actually theoretical studies of ENSO that has been showing and acknowledging that ENSO is characterized by a wide range of regimes, especially, and a strong temporal complexity or irregularity. So, for example, let's have a look at this so-called ENSO complexity. So first, the spatial diversity. Here you can see the first two dominant mode, EUF mode of SST anomalies over the past 4 years, I think. So the first mode that emerged and that explained most of the variability is, of course, this canonical ENSO dipole pattern with like warm temperature on the east and cold temperature on the west. But a significant portion of the variability, up to 10%, is actually associated with another recently documented regime of El Niño, which is the Central Pacific, or the El Niño Modo P, you may have heard, which is characterized more by sea surface temperature anomalies concentrated in the Central Pacific and flanked on both sides by polar anomalies. So we might not explain much of the variability, but recent studies show that this pattern of variability will probably be the dominant within the global warming. So that's the spatial diversity of ENSO. Now let's have a look at the temporal irregularity. One way of looking at that is by simply looking at this Niño 3.4 SST anomalies, where we can see actually much stronger El Niño than La Niñas, but they're shorter lived. So we have like a very strong, intense El Niño that's not going to last much longer. Whereas La Niña is a little bit smaller, but tend to linger in the Pacific and sometimes up to 2 or 3 years. So you have like both this amplitude and temporal ENSO asymmetry. Another irregularity that we focus most of the talk on is the seasonal El Niño synchronization, which is a complicated term to basically just say that ENSO always arrive at the same time. So here it's illustrated here by this the Niño 3.4 monthly climatology in blue, and in red the monthly variance. So we see that the monthly variance peak in the boreal winter, the GF, when the sea surface temperature are the polar, so which will lead to a much increased anomalies. And that also will lead to a seasonal modulation of ENSO impact. Since ENSO comes all the time at the same time, the impacts will be seasonally synchronized with this interannual variability. And this also will provoke nonlinear interaction between the annual or climatological seasonal variability and the ENSO interannual variability. One simple way to look at that is actually to look at like two sinusoids that will interact within each other. So the product of two cosine functions, one blue here at the 12 months period, which represents the annual cycle every 12 months, and one here at the ENSO period, which is like simplified here at just a 36 months, 3 years period. Like when you multiply two cosines, you make appear two new frequencies that are the sum and the difference of the overall frequency. And those frequencies emerge deterministically. You can predict them. So that's the seasonal modulation of enzone impacts. Let's have a look at how that translates for pulsar waves. So we've seen that earlier in the introduction that ENSO will modulate the tropical cyclone activity and intensity. That will occur, of course, in the summer when the tropical cyclones are more active, season. Also, this modulation will be different depending on which kind of El Nino we are on. Either Eastern Pacific or Central Pacific will have different impacts on the modulation of storm activity. So you have like a very different teleconnection depending on whether you are on one kind or the other type of ENSO. So there are this summer modulation. Of course, in winter, we'll not go into the physical details of that, but like El Nino will also modulate the jet stream, the storm track, which is where most of the extratropical storms are born, with El Nino basically provoking a downward, forward movement of the jet stream, which tend to extend actually all the way over North America and into the Atlantic Ocean. Whereas during La Nina, we have a more meandering jet stream pushed up forward. So that will modulate both the spatial pattern and intensity of the extratropical storm formation. And of course, those pictures will be different depending on if we are on the Eastern or Central Pacific. So essentially, there's like two routes from which ENSO will modulate the coastal wave activity. It's in summer through the modulation of tropical storm, and in winter through the modulation of extratropical storm. So those are like the main mechanisms. I will try to put into a very simple equation to see if the math can actually help us simulate and forecast those kind of impacts. So I'm gonna basing the rest of the rotation on a very simple model, very simple equation, which is the stochastic climate model from Klaus Hasselmann, German scientist that got the Nobel Prize in physics a few years ago, not just for that, for his career. And this simple equation is shown here. Basically, his idea is like very simple, pretty elegant, if I may. It's just like you can see a prion, the atmosphere, are constantly generating random noise, short-lived random noise. But that noise over the ocean, which has much stronger inertia, the ocean will actually not respond instantly to every single noise. Rather, it will accumulate this noise, integrate them over time to produce a deterministic low frequency or slower response to those atmospheric noise. So this stochastic forcing can actually generate a well-organized climate variability at lower frequency. So let's try to put that for this framework, apply this framework for coastal wave. So essentially, we have the wave that we can see as an oscillation, the return period of essentially every 2 weeks. So we have like every 2 weeks on average throughout the globe, we have one tropical cyclone in summer every 2 weeks. And the same at the high latitude, every 2 weeks on average, we have an extratropical storm that propagates. And then the activity of those storms will be modulated by a stochastic forcing, the random occurrence of storm, as well as a climate forcing. And we've seen the climate forcing at those scale is actually controlled by the seasonal cycle. Summer, we have the tropical cycle, in winter, we have the and by the ENSO variability and the two types of ENSO. So here we have two indices actually represent those two kinds of and I've shown like a couple of years ago that this equation can actually be integrated and solved numerically, but also analytically. And the analytical solution can be actually seen as that. So it's not the wave per se that we resolve, but rather the amplitude, modulation of amplitude of wave activity, which is over that form, which is actually express itself as a sum of direct linear forcing. So we have the direct linear climate effect, summer, winter, and so we have a direct effect. We also do have this m squared term, this nonlinear interaction between those time scales. So we have the interaction of the El Niño annual cycle, producing like this, the emergence, the deterministic emergence of a new time scale, near annual time scale, through this isosynchronous synchronization. So let's have a look at how this model performs. Here I can show you the uncast from era 5 of the wave energy, which is the wave height squared times peak period, in Southern California to San Diego. And we have the interannual anomalies of this wave energy. And in blue and red, the solution of this model. So in blue, the solution of the model only takes into account the canonical nu and just its linear effect. Whereas in red, we account for the entire solution of this model, including this m squared term. You can see that we have an increase in progression from 0.5 to 0.7. We are able to reproduce those big linear events, as well as this very fast wiggling, near annual wiggling that the short-term near annual time scale variability, that the linear effect is not sufficient to account for. So we have this small, very simple equation that can help us to simulate and anticipate the modulation of coastal wave activity in the Pacific. And I will show you that we can actually extend this framework beyond the Pacific in other ocean basin as well, and as well as on the other drivers of coastal vulnerability, which were, if you remind, the sea level and the river discharge. So let's have a look at, and also like directly on the coastal risk indicator. So let's have a look at one indicator of coastal risk. So that's been a big work that has been developed in one of the team in Lagos, the littoral team, trying to assess through remote sensing the position, the evolution of the position, the cross-shore position of the shoreline. Here you have the shoreline, and depending on the time, you can either have a retreat or an advance of that shoreline. Retreat meaning an erosion, advance meaning accretion of sediments. So what we've been doing, so you can of course do that through video monitoring, LiDAR, but that will only be possible to do that on specific sites. If you want to assess at the basin and the global scale, you will need, of course, to use remote sensing. And a very simple technique, actually, like for every image you get from your satellite, you can calculate the normalized difference water index, which is a way to evaluate if one of the pixels in your image is actually corresponds actually to water or land body. So if this normalized difference water index is positive, essentially you will have water in your image. If it's negative, you will have land. And by simply defining the interface between positive and the negative NDWY, we can evaluate the shoreline condition. And if we do that over multiple satellite missions, we're able to actually reconstruct the monthly composites of the shoreline globally. And we've been able to do that all along the global shoreline at a long-shore resolution of essentially 25 kilometers from 93 to 2020. So we can actually assess the seasonal variability and the interval variability of the shoreline position pretty much globally. So let's have a look at this data set. So that's from a very recent paper that we've done with a PhD student. So it's this shoreline. Here you can see the shoreline. That's in again San Diego, Torrey Pines, where you can see the average yearly condition of the shoreline, different years. And here in black, you can actually see, you can see 2015, which corresponds to El Niño, which is way more inland. So the water is more inland. So I mean, it's like shoreline position retreats with all the associated risk of erosion. And here you have, through that product, you have the seasonal waterline excursion, which is basically the seasonal amplitude. We have a strong variation, seasonal variation in the northern West American coast, and when we go south, the seasonal variation is more smaller. So here you have like this waterline position all along the coastline with red meaning advanced, so accretion, while blue means potential erosion and a retreat of the shoreline. And here we can see, for example, in the northern part of the domain, that this shoreline position is actually dominated by the wave power. Strong correspondence, strong correlation between wave power and waterline or shoreline position. Whereas in the southern part of the Baja, the wave power doesn't exhibit much amplitude modulation. Instead, the sea level, the regional sea level, will be more instrumental into determining the seasonal variation of the position. So we have two different regimes: a wave-dominated shoreline position regime in the north, and as soon as you go towards the tropics, it tends to be more related to sea level, regional sea level variability. So the shoreline drivers, as a reminder again, is mostly three drivers: wave energy, the sea level, and the river input, the river flow input that kind of control the amount of sediment you get to replenish your beach and your coastline. So I presented you the very simple model actually account for wave amplitude modulation. Let's do that the same on those other the same model. Let's do that on the sea level and the river at the global scale. So here I show you the correlation between the interannual anomalies of sea level, wave, and rivers, as observed through a bunch of different reanalysis products, and as simulated again by my small Hasselmann equation. So we can see, of course, a strong correlation within the tropics at interannual time scale, where answer will be the dominant source of variability, of course. Same for waves, same for river. But we can see that we still have like significant correlation. That's the one only significant here that extend into other basins like in Indian and the Atlantic basin. We still, this small equation is still enough to explain this interannual variability of those drivers. So can we say that this small equation can explain the driver? Why not skip the driver altogether and just try to apply that to the shoreline position, to the data set I've been presenting you? And again, it kind of worked not too bad. So we apply the same model, but to the shoreline position. And again, we see like stronger correlation within the tropics associated with the ENSO signal, but we also have like correlation that extend to the higher latitude and to the other basin. It is also on the very spectrum of significativity in a bunch of places. I have to admit that. And even in Europe, it's not significant at all. We have like part of the world that this simple framework is not enough to really understand variability. So in other basin, we can expect other modes of climate variability to actually play a role. And that's what we've been doing with a couple of students a couple of years ago. We've been looking at other modes of climate variability. I showed just a couple here. The northern North Atlantic oscillation, which is an expression of extratropical variability in the Atlantic. The IOD, which is the variability in the Indian Ocean, and the southern annular mode, which is the extratropical variability in the Southern Ocean. So we've been looking at like which kind of modes control more coastal sea level, wave, all this kind of thing. And here I present you the dominant mode that explains the interannual variability of sea level anomalies. And we can see here that where we are not good with this simple model, it's because most of the variability seems to be related to NAO, which is not accounted for in this model. So we just decided to put it into this simple model by simply integrating linearly, very simple, integrating those climate modes into this equation. So we just add the linear function of the climate mode indices. into this simple equation. What that gives us, it's the correlation increase between the model without and with this climate mode. So we can see a very significant increase in correlation between the observed and the simulated shoreline position, essentially in the North Atlantic and the Mediterranean. So yeah, this simple linear inclusion of climate mode will substantially increase our shoreline simulation outside of the Pacific as well as towards the higher latitude. So still, when we count of diversity and complexity, it seems to influence coastal hazard beyond the Pacific, but it's not the whole story, and we have to account for other climate modes, as well as, I will show you in a second, their interaction with each other. Because, right, and so cannot be studied in isolation of those climate modes, because as a far-reaching phenomenon, it will interact and influence other basin, as well as the higher latitude, through both oceanic and atmospheric teleconnections. So one simple way of looking at that, it kind of also can provoke link between the tropical basins, the other basin, the Atlantic and Indian Ocean, through the redistribution of the Walker circulation and the convective patterns associated with that. So this Walker circulation shifted and reshuffled by ENSO can actually move and impact on one side the Atlantic basin and on the other side the ocean. So it will impact the tropical mode of variability associated with each of those basins, which is the Atlantic El Niño, the Atlantic El Niño ocean dipole in the Indian Ocean. Similarly, ENSO will also reshuffle and shift the Atlantic circulation, which is the meridional circulation, like redistributing it between tropics and extratropics. And that will have more of an impact on the meridional mode. So North and South Pacific meridional mode. So those tropical modes are more, the expression is more zonal redistribution of heat and convection. Those modes are actually more meridional with tropical and extratropical extremes. So the question is like, can we improve those seasonal forecasts or this seasonal to interannual modulation of climate of coastal risk if we account for not only ENSO, not only the other linear influence, but also this teleconnection, this interaction between all those modes. So I'm going to try to show that to you on a different coastal risk indicator. So we've seen before the shoreline position, which is kind of a proxy of erosion. Now I'm going to show you a proxy of flooding. So for that, we've also been producing very nice data set that we have at Lagos now, which is like a proxy of potential coastal flooding that we get along the global shoreline. So what we decided to do is like take all the components of coastal water level, which include the sea level anomalies, the tides, the wave runoff, which is the sea level induced by breaking wave. There's a parameterization for that. I will not go into details. And we have all those data sets at an hourly resolution. And when we sum them all together, we can compare the level, the coastal water level, to the topography. And we decided to say, okay, when our total coastal water level reach a certain threshold of the topography, of the maximum topographical elevation within the first kilometer, then we have the risk of flooding. So we can count essentially the number of hours per month where we are at risk at flooding, where the coastal water is higher than a certain topographic threshold. And the maximum elevation you can see here, it's pretty high in Barra, so okay, so earlier I showed you that when we were including the North Atlantic oscillation, we were able to increase very substantially the modulation of shoreline erosion in the Northern Atlantic. So I will focus on this very specific climate mode interaction between ENSO and the NAO, which is so it's the effect of ENSO not only on another basin, but also on the higher latitude of another basin. So it's more kind of the most complicated case. So here you can see it's a composite in hours per month of the interannual anomalies of this climatology. So it's the anomaly, the number of months above the climatology in terms of potential coastal flooding. And that's a composite during the Central Pacific El Niño. So we can see that we have a strong increase in potential flooding along the coast of America, of course, associated with this increase of wave, this increase of sea level anomalies. And we have not much of a signature in the rest of the world, and in particular, not at all in the in the Atlantic Ocean. That's the composite during the Central Pacific El Niño. Now let's have a look at the composite during different phase of the North Atlantic Oscillation. So the North Atlantic Oscillation is this meridional mode that kind of control the position and the strength of the jet stream in the Atlantic Ocean, with a positive NAO phase intensifying the wind and the jet stream position here, and leading to an increase of potential flooding over Western Europe and Scandinavia, whereas a negative North Atlantic Oscillation we kind of block these storms to come in the north, and we'll redirect them towards the south, south of Europe, Mediterranean, and even to the Western African Peninsula. So we have like this dipole, or like stronger coastal flooding, NAO, and stronger flooding into the Mediterranean during the negative NAO. Now let's have a look at when those two modes interact, when they co-occur, when they arrive at the same time. So here you have the co-occurrence of coastal flooding during co-occurrence events of positive NAO and Central Pacific El Niño. And you can see that those patterns are increased, and actually they are more than just increased, and they are more than just the linear sun between them. So there's like different statistical tests to see that, but we have a multiplying effect between the NAO and the Central Pacific, which kind of non-linearly amplifies the possibility of coastal risk, whether in the Pacific and in the Atlantic. And again, the same picture during positive El Niño and negative La Niña, with much stronger risk on the eastern seaboard of the US and much stronger risk in the Mediterranean. So we have this nominal amplification of coastal flooding. So that tells us that you cannot look at those modes independently. You need to look at them together and interacting between each other. So we've seen that ENSO interact with NAO. That leads to amplifying impacts in the northern Atlantic. But of course, ENSO interact with a bunch of different other climate modes. I'll show you some of them here: the tropical North Atlantic, Atlantic El Niño, IOD. And with other students, we've been looking at this interaction. And we've seen that actually part of the local variability of those modes could be interpreted as the seasonal modulation, the local seasonal modulation of ENSO. So in other terms, a significant portion of the variability of this mode can be apprehended through this ENSO annual cycle interaction. So this deterministic combination mode interaction. So what that means that we can again apply the same very simple Hasselmann type model to explain at least significant portion, a nice portion of the variability of those modes. So we can do that. We can apprehend through a simple equation this teleconnection, this interaction between ENSO and all those modes. And we can also couple that, so that's been done by colleagues in Hawaii, with a very simple discharge ENSO dynamic that I was telling you about at the beginning of the presentation, which kind of just couple the sea surface temperature surface and the subsurface thermocline depth dynamic. So there's a very simplified model with two equations that kind of couple these two to produce this recharge-discharge pattern associated with ENSO. So that's been done, and that's has been published recently in Nature. It's the extended recharge oscillator, and that has been shown to significantly increase the ENSO prediction, as well as significantly increase all the prediction of those other planet plots. Here you can see that's the correlation scale of this model in function of the lead time. And you have X arrow in black that kind of produce very significant forecasts up to 13, 14 months in advance. And it's actually pretty good that it actually beats AI always. So okay, we have like this XRO oscillator, and we decided actually why not use that to account for ENSO and the interaction, ENSO nonlinear dynamics and ENSO nonlinear interaction with other climate mode, and try to apply that directly to our shoreline position and coastal flooding indicator. So for very simplified, very simple way of looking at that model, I will not go into the details. Basically, we have like state variables that are the state of ENSO, which is the sea surface temperature and the depth of the thermocline. We have all our other climate modes that I showed you before. And we also included the coastal flooding time series all along the coastline. And variation of those guys depends on a linear operator. Here, L, which is the ENSO dynamics, the Hasselmann dynamics for the other climate modes, as well as the coupling between ENSO and the other climate modes. The effect of ENSO on climate mode, and in return, the effect back of climate mode on ENSO. We have also a nonlinear operator and stochastic forcing as well. So we use that model, and we actually trained that model over 1958 to 1992, and did forecasts for coastal flooding over the remaining of the period, 1993 to 2023. So those are the regions I actually focused on in the paper: Western Europe, Mediterranean, and Eastern and Western. So here you can see what we did every month during 2023. We initialized the prediction, and we let our model run for like 12 months. The prediction are shown at every initial condition. Those are the little red spaghettis, and the blue is the actual observation. It looks like kind of okay, but like we want to do some statistics on that to see its significance. So here, for each region, we have in blue the ACC, the correlation coefficient between the forecast and the observation as a function of the lead time after initialization. And in red, you have the working square difference between the forecast and the observation. So basically, like due to El Niño, of course, the dominant source of predictability in the western coast of America, we have a very good score up until 6-7 months. We go a little bit down, of course, in the North Atlantic, because North Atlantic, governed by NAO and atmospheric processes, is much more chaotic. But we still have some kind of significant forecasts up until 4 to 5 months, which can give enough time for stakeholder to potentially prepare. So there was like this paper that we published like this year, which emphasized that this nonlinear climate interaction are instrumental into selling impacts and potentially the predictability. So those are. It's a nice way of summarizing that. I asked ChatGPT to help me produce a nice figure rather than speak 1,000 words. Essentially, we have ENSO as the conductor of the climate variability, the climate symphony. Okay? The seasons will set the tempo. It's going to be the pacemaker, and we will have coastal risk that follows essentially through a seasonal modulation of ENSO associated with each of those basins, and in turn for coastal risk. So that's a very simplified framework. Of course, it's pure math. It gives us a nice outlook on how ENSO and the nonlinear interaction with climate variability can actually shape coastal risks throughout the world. But we don't know, that doesn't answer about like which are the physical mechanisms involved. 5 minutes, perfect. So the math are one thing, the physics is another. And I agree that if you really want to understand the physics behind all that, not just the math, you need to switch from a more conceptual framework to a more realistic framework. And that's, you know it, ocean, echo, atmosphere, wave, warmth, and then you couple that and you play with that because you can play with it. It's fun, right? So that's what we've been doing with a postdoc with Lionel. We've been setting a nice configuration over the tropical Pacific, coupled between Coco and Wharf. And what we can do with regional couple modeling is we can play, do sensitivity experiment, change power recognition to actually control what kind of variability will come into our model. So we can have like completely realistic if we constrain with R5, glorious, whatever. We have the realistic condition, oceanic and atmospheric, getting into our model. So that's control experiment. If you can stop that and just put the climatological, so you don't have any internal variability coming into your model, so you can actually access the internal tropical variability that is actually generated within your model, and you can alternate that, putting realistic variability along the Atlantic and Indian, the western and eastern boundaries. So you can completely shut up the tropical and extratropical interaction. So assess what is this interaction between basins. But the opposite, we can do that. Climatological on the western and eastern side, and look at the realistic condition getting in north and south, so you can have a way of diagnosing the tropical and extratropical connection. So we've been doing that. We have like very preliminary results. So here, like you have the difference in mean state between the control run and the node tropic, extratropic. So essentially, that's change in mean state will be due to what's coming in from the Indian and the Atlantic Ocean. And below is the change in mean state associated with what's getting in from the north and south. That's very, very preliminary, so we have no clue what's going on so far. Another perspective of that work is operational seasonal forecast, trying to generate like seasonal forecast on an operational mode with our coastal XRO, relying on the center forecast. And here, just to please Julien, I wanted to talk about this Super El Nino. Is it really coming or not? Is it a scam? Who knows? So here you have like the latest forecast initialized last week by the European Center, and we can see that huge spread still, but in the higher part of the. So yeah, I mean, it seems to be coming. And if we have a look at the local condition, here you have the zonal wind, the sea surface temperature, and the thermocline depths over the last 2 years. We can see that we are definitely much more in El Nino condition than last year. Okay, that's no surprise. But we had like a very strong westerly wind burst that triggered flattening of the thermocline associated with heat content and anomaly here. So we are good. So seems that we are getting this El Nino coming. Let's have a look at the very latest condition during this week. And we can see like it's the daily SST anomalies for May the 3rd. And we can see like two spots that looks to be a little warmer than usual, warmer than actually the warmest around it. And if we look at the tail data, we can see those patches of like warm anomalies and westerly anomalies. So like the airness feedback seems to be still kicking. So yeah, let's see. You might be actually getting a boson Kelvin wave in the coming weeks. Yeah. So that means warmer temperature. So we have EXO probability of like 90% for the next few months. But if we look, that was the SST anomaly. The NOAA actually now produces forecasts for the relative SST anomalies, which take into account the global state of the Pacific. So you remove the area average, either the global mean temperature or the tropical mean temperature, basically remove any kind of signal from very low frequency variability as well as global warming. And when you do that, you see that you're not that much into a warming phase. It's warmer than usual, but it's much lower than the normal SST. So let's be careful, because when you look at the forecast updated very recently by the Americans, here we have the forecast using an ENIO 3.4 SST anomalies, and you say, okay, sure, it's big El Nino coming. When you look at the relative SST, it's big El Nino, it's El Nino is coming, but it might not be as big as hyped by the media. So that's why the strong, if you look at the relative El Nino 3.4 index, you just have a 20% of chance of having a very strong El Nino. And a word of caution to conclude: stronger events do not always mean bigger weather impacts. They just make it more likely to occur. So all what I said, just take it with caution. And also we're still in the spring predictability barrier. So let's have a look at the next visualization of the forecast. Thank you very much.
Excellent. Thank you so much, Julien, for your talk. And so we have plenty of time for questions. So we're going to start here at the auditorium. And if I see students wanting to ask, they will go first. Okay, then students or no students. Okay.
Okay. It's a very nice talk, and you have really covered lots of topics from climate to ocean. But there is something that you haven't mentioned. It is the interaction with decadal to interdecadal variability, especially in the Pacific, with the Pacific decadal oscillation. What are your comments about that?
Well, so we have looked at this. So that's funny, because when we we did some experiments in the XAERO model, like by specifically putting the PDO and also the AMO, the multidecadal oscillation, and we are able to increase the predictability and the slow frequency variability very well. But it's really hard to know what's actually associated with. I mean, like, this decadal variability is such a tricky subject for me, because like is it just a decadal modulation of ENSO, or is it something completely unrelated that kind of changed the background? I'm not sure about that, but like, for sure, when we put those low frequency climate indices into this kind of framework, you get better correlation. But like, how artificial is it? Like when you look at back in the days, yes, you have those video record, but like when you do forecast and projection, I mean, how much is it from the decadal signal? How much is it from some progenic signal? I mean, it's definitely something very interesting to investigate, but it's a complicated subject.
Anyone else here? Yes, Pedro, here.
Thank you. It's very impressive and very global, everything. But I was wondering about the how you define the ocean and the land in this. Like, it feels super specific and very difficult to automate it. And also for the flooding risks, like you have this height difference, but where do you decide? Like, from what data? How do you know these things? It must be very hard.
It is really hard. So what you have to keep in mind is, like, when we produce this kind of data, those data are like, they don't work at your local scale. They don't work for your local beach. They don't work for your local coastline. But they do work when you average over like specific, like, let's say couple 100 kilometers region. So it's good for like regional seasonal outlook. It is not yet good for like very precise beach specific thing. But interestingly, like actually what I presented over the North American coastline, it was much higher resolution data set that we've been able to produce just over the past 10 years using only Sentinel-2 and other satellite mission. And we've been able to actually pinpoint, and we have like a 2 or 3 kilometers resolution along shore.
Okay.
And we've been able to actually compare that to, there's not that many in situ data for shoreline position. And it's really hard to compare because they all have the specific way of measuring it. But still along the coastline, actually, we took the data from Barra, California. I don't know where they are exactly measured, but like we were able to have data from here, from San Diego, from USGS for Portland, and actually they match very well with the in situ and the satellite data. But like there's a lot of things to do, like correct the tides. It's complicated. That's why we have a PhD student working on that.
That's what we do best. Yeah, because I was thinking that you must just get like how big, if you say flooding, like what does that flooding mean? Then it must be hundreds of kilometers of flooding that you're talking about. And like, it's very like intense scales. But I mean, it's good to be able to predict them. No?
Flooding, I mean, we need to assess again, like this continuum between bathymetry and topography. So that has been, in that data set, it was from satellite. We want something like digital elevation model. They are what they are usually. The thing is like the error bar is like 10 to 15 meters.
Oh, wow.
It sucks, you know, like when you have like that much variation and that much error, you know, on a specific site, impossible.
Okay.
When you average over a region, it starts to get significant again. But if you really want like this continuum and be able to look at the coastal water level compared to the actual topography, you need a LiDAR or like video instrumentation.
Yeah, of course.
Or something
you need
like
to
that.
go there and look at it.
Yeah. But we also do that on specific sites. This approach is more like, it was just like more a fun game to play, you know, and trying to have global, this kind of global data set. And we actually pissed off the geomorphological community that has been working on their specific beach, and we arrived with a global data set, which is what it is, you know, but like we've been able to actually disentangle climate phenomena. I have a sufficiently long record to actually be able to look at ENSO and seasonal variability.
But it's very cool.
Thank you.
Yeah. Hopefully it will be more higher resolution later. Thank you.
Okay, so Paula.
Thank you. That was very, very interesting. And I was wondering from the mathematical models, the last one, which is the more complex one. I mean, if I understood right, all of them are based on some indexes, right? But like, how do you? I don't remember how the coupling goes with the But like, how do you? The one that has the nonlinear interaction between the different climatic modes, like that L thing, that the C1 and C2, how are those indexes too? Where are those?
Well, the C1 and C2, they are actually they're estimated to the data. That's why, like, we estimated like those copy coefficient on a specific period. So we have like I'm not quite sure. Like I was not involved completely in that paper. So we have like here it's the Richard discharge dynamics, like the very simple equation between T and H. Here is the equation I showed you before. You know, like with slower this central damping. SST. The C1 and C2 are actually data, estimated through the data to maximize the correlation between the observed and I think it's like you're right, the climate indices. Yeah, we've been estimating those two. I don't remember exactly how they did that because like it's really those coping coefficient. I think it's just that data estimated from. Yeah, so we've done like like estimating all those parameters onto different period that we actually forecast, or we do this leave 1 year out thing, so we can try to forecast 1 year, which has not been used to train the model. So yeah, that's this model is the strength of this model is actually to just combine these different kind of dynamics, the very deterministic ENSO dynamics plus the more statistical kind of Hasselmann dynamics, other climate modes. But you know, again, just like what I presented before, the strength of this model and all forecast model comes from initial condition. From the initial conditions. So we've seen that with the wrong ENSO initial condition and the right NAO condition, we're still not able to predict what's going on in Europe. So it's still ENSO against the dominant source.
Anyone else? Pueden también hacer sus preguntas en español. Julien is able to catch the questions in Spanish.
Hi, thank you very much for the talk. I wanted to know if you could briefly comment on asymmetries between the response of El Niño and La Niña. I suspect that you don't just get the opposite or no. Regarding the things that you have studied.
Well, you're right. And so it's characterized by this strong asymmetry, and and this asymmetry translate into the impact. So the asymmetry is also something very, very timely. Like that's what we are still investigating. Where does this asymmetry come from? That's also that's all you have. All nice, complicated questions. But this asymmetry between El Niño and La Niña translate directly into impact. But I would say El Niño is very much stronger than La Niña, so you might expect stronger impacts. But La Niña very mellow impact. But keep in mind that La Niña lasts for longer. So just in terms of insurance money, La Niña is more costly than El Niño because you have like those lingering impacts, and especially in the Southwest Pacific where you can be in La Niña condition, even if they are mellow for like 3 years in a row, which will trigger like fire and what that can actually be recurrent over 2 or 3 years. So in terms of if you integrate the amplitude and temporal asymmetry of El Niño, strong El Niño, mellow La Niña, but long La Niña and shorter El Niño, it kind of balances out at least the impact on a very integrated measure of economic insurance money.
Any other question? Yes, Tere.
Hi, thanks for your presentation. Very interesting. We know that the El Niño and La Niña have different impacts depending on seasonal on the seasonal feature, and you mentioned that is the peacemaker. El Niño has a stronger influence on winter storms, and La Niña on summer storms. So your analysis separates that different influence, seasonal influence?
Actually, El Niño and La Niña, I mean, if you say that El Niño and La Niña is the peak of either the warm or the cold phase of the oscillation, the warm peak and the cold peak all occurs in winter. So you will have the strongest impact, whether it is an El Niño or a La Niña, in winter. And then you will have the stronger impact on extratropical storm during this boreal winter. But El Niño and La Niña also do have an impact, not at their peak, but also during either the onset or the decay period, which occurs in summer, and which will have more of an impact on tropical cyclones. But El Niño and La Niña, the peak of what we call El Niño and La Niña, always going to happen in November to February, so always going to be in winter.
Okay, thank you.
I have a simple one. What's
I'm afraid.
No, what's the explanation for the significant wave height pattern during El Niño and La Niña, particularly, in the extratropics? Because if the wind, if the jet stream goes down, I mean, if the jet stream is in the upper atmosphere, but anyway, what's the explanation?
The jet stream wiggles like back and forth, but like you have the jet stream in the upper atmosphere, but it changes also the storminess at the lower level atmosphere. So like if I had like I didn't put it in the talk, but I had so yeah, the El Nino, how does that work? Like you have like this going down of the water circulation, the effect on the Atlantic circulation, and like essentially like a very straight jet stream just moving south, which south and west. So like it kind of like brings more what's the name? Aleutian low. The Aleutian lows comes closer to here. Whereas during La Nina, this is not the best view, but like the La Nina pushes northward and like make it meander. So you have like the Aleutian lows shifts here during El Nino and more here during La Nina. So you have more like northwest and northwest swell during El Nino that are allowed. I mean, like they can basically travel all the way to South America. Whereas during La Nina, those swell are actually more contained in the western part of the basin.
So it's still swell coming from the north, a reduce or increase, but it's from the north.
Yeah.
It's just that I was. Yes. Okay.
That was it.
Any más? Yeah.
About the prediction of the 2026 El Nino, how does El Nino index integrates climate change?
But that's.
And what is I know that there's different indexes for El Nino. Is 3.4 the best index for these kind of predictions?
That's the best way to integrate climate change. It's like the relative SST anomalies. So you take your classic SST anomalies, where you remove the tropical mean average, or I don't know if it's the tropical mean or the entire global mean SST.
Oh,
okay. It's the simplest way we can have to just remove those classical patterns. When you look at the index, that's the forecast of the same Nino 3.4 index, the classic one. And here it's the Nino 3.4 corrected, the relative Nino 3.4, which is corrected from global warming and anthropogenic pattern. And you see, if you take a little bit, if you remove some of the heat that would be accumulated anthropogenically, you see that comparatively the forecast is a little weaker. So the ensemble mean is above +3 here, so like super strong El Nino, whereas here we are like barely just reaching 2.5. And for which index is the best, I mean, really depends. El Nino will be characterized by variability using different indices, and like different indices will tell you more about regional aspects. And so Nino 3.4 is like very Central Pacific, so the one that explains the most the atmospheric response in terms of precipitation. Well, if you want to look at, I don't know, fisheries around Barra or Peru, maybe Nino 3 or Nino 1.2 would be a better index to evaluate more locally the impacts of it.
Thank you so much.
Okay, second round for Paula.
Just a comment from these and from what you were saying. This is what gets me very confused nowadays because it has also to do with, for example, the definition of marine heat waves and everything. The fact that we're like going into a hotter time and there's a trend, you want to remove it to see the other variability.
Yeah.
But in the end, the effects are going to be the ones with this temperature. So what does this mean? Is it like you want to see the El Nino compounded with a global heating trend, or is it an El Nino that, like, supposedly you extracted the dynamics from the El Nino here to say that is
In terms of
not a
impact,
super Nino, but like hot climate?
you're right. In terms of actual temperature, they're much warmer. Like if we have to take everything into account. Instead of dynamics, I'm not sure because, like, you know, like for the Bionas feedback to kick in, or like for the dynamics, it's like zonal contrast in terms of anomalies. So we have to remove that. So there's the dynamical part, which we need to predict or forecast. In terms of actual effect, you're right. I mean, like for like ecosystems, fisheries, whatever, we need the actual temperature measured at the time. But for like the relative SST anomalies, like I think it's a better way to assess the dynamics, and so.
Anyone else in here? I do have one, like a very quick one. I don't know if I saw it correctly, but if you can go back to your slide where you have the interaction between ENSO and the two phases of the NAO. So I think you do have the 5 plots, because I believe I saw like that one, I think. So the vectors are those winds, right? And so in either the positive, well, I guess it's more clear in the positive phase of NAO, if you see south of Alaska. So I think, yes, in the Aleutians, yes. So you see the winds going in this direction, right? So in the...
I don't think it's much. I mean, like the effects... Like the response of NAO is more concentrated here.
But in both cases, sorry, either the NAO and the El Nino, so you have a different circulation to what you have in the composite. So I was just wondering why that is, because I see it's like quite opposite. If I see correctly, that one there, yeah.
Yeah, so you have like this.
Yes, exactly. That one goes in the other direction. Yes.
Yeah.
So the two of them, that looks to me. So I'm just wondering if there is like anything that could be, even though you're accounting for the two effects, there seems to be something non-linear that might be, or is this?
So something also here, like
anomalies.
We only have that many events. And like, so it's like from 58 to 2023. So there's a few events, but like the thing is, also what I didn't mention is like this interaction is actually very much increased during strong El Nino events. So you might have also we only have like 2 or 3 strong El Nino events, which is not enough to really assess those interactions between, because like this interaction might be it's not like a matter of type of El Nino, it's a matter of amplitude of El Nino. And only, I would say, like, I mean, this thing, like, maybe was not the best example, the C+, because those are not the ones which reach the maximum amplitude as compared to the Eastern Pacific. And the Eastern Pacific has even stronger impacts than that. But I would not be so confident about like how significant that is, because we only have 3 of those. And that's something we want to look at, like this ENSO-NAO teleconnection in long-term AMIP simulation, where we have like multimodal approach and we have longer time series.
Right. So
to actually, like, we've been looking at like people who've done that, and like you have like this, seems like this ENSO-NAO teleconnection seems to be kind of significant, but the significance is mostly due to the amplitude and during extreme El Nino. So that's why, like, I mean, when you look at Central Pacific El Nino, and especially going back in time, who knows about like how AR5 simulates atmospheric response.
Might not be.
We take that with also with
Correct.
question.
Sounds good. Okay. If there is anyone online who wants to ask one question on Zoom, we don't have anything from YouTube or any other at the moment. Or any final here? Okay, because if not, as always, we will have the queso pan y vino outside. And we would like to thank you, Julien, so much for your time.
Control.